Hi everyone, in this tutorial we'll discuss the effectiveness and efficiency of a fin.
Effectiveness of a fin is defined as the ratio of heat transfer with fin to the heat transfer without fin. Now, the heat transfer from a fin with end insulated. Let us take the case where end of the fin is insulated or negligible heat transfer from the end. You get the heat transfer through this kind of fin as KAC theta 0 tan HML. That's what we have studied in the previous class. So when end is insulated or heat transfer from the end is negligible, the heat transfer with the fin is KAC theta 0 tan HML. So heat transfer with the fin, taking that, neglecting the heat from the end, we get KAC theta 0 tan HML. That is a heat transfer when the heat flow from the end tip of the fin is neglected or assuming that it is no heat is flowing from the end. Now, heat transfer in the absence of fin. So if I remove the fin, this is a fin, I just remove the fin from the surface. Okay, so this is the area occupied by the fin. This portion is the area occupied by the fin. The heat flow from this area, if in the absence of fin, if a fin is not present, in the absence of fin, the heat flow would have been by convection from this area. So what will be the heat transfer from this area? Convective heat transfer. It is HAC theta 0. This area is AC, area of cross section of the fin. Okay, AC. So as per Newton's law of cooling, HA delta T is the heat transfer by convection. H is the heat transfer coefficient. Okay, so H into area is AC and theta 0 is the temperature difference. Theta 0 is the temperature difference at the base. This is the base. The fin is attached to the base. So here the temperature difference is, base is at temperature T naught, ambient is at a temperature TA. So the temperature difference is T naught minus TA, which is theta 0. So in the absence of fin, the convection from this fin occupied area is HAC theta 0. But when you provide a fin, the heat transfer is KAC theta 0 tan HML, neglecting the heat flow from the edge. And this ratio will give the effectiveness of the fin. So effectiveness is what is the heat transfer with the fin and divided by the heat transfer without fin. So you get this equation and you can cancel theta 0 and AC you can cancel. You get Km by H. Okay, cancelling AC and theta 0, you get Km by H tan HML. So that is the effectiveness of the fin. It shows how many times the heat transfer is increased by providing a fin. In the absence of fin, the heat transfer from this area, if it is 5 watts, and by providing the fin, if the heat transfer increases to 25 watts, then the effectiveness is going to be 25 by 5 or 5. By providing the fin, 5 times the heat transfer has increased. So effectiveness means how many times the heat transfer is increased by providing the fin. So always the intention of providing a fin is to increase the heat transfer. So by providing the fin, the heat transfer only should increase. It should multiply. If it reduces, that means it is blocking the heat flow. So effectiveness, if it is less than 1, it is by providing the fin, the heat transfer is getting reduced. So this is not advisable. Always the heat transfer should increase and then effectiveness should be always greater than 1, and that is desirable. So I hope all of you understood the effectiveness of a fin. Now another term is efficiency. When you talk about the fins, apart from effectiveness, another term used is efficiency. It's defined like this. Efficiency is defined like this. It is the ratio of heat transfer with fin to the heat transfer from the fin's surface when the entire surface is maintained at root temperature or base temperature. So it is defined as ratio of heat transfer with fin divided by heat transfer when the entire surface of the fin is maintained at root temperature or base temperature. Okay, so numerator is same here. For effectiveness also we add heat transfer with fin. Okay, but denominator is different here. I'll explain this, the denominator part. This is the base from where the heat is flowing. So the red plate shows the base, and base temperature, let us assume it's at higher temperature. So the base temperature is high. So now I have divided this fin, which is circular in shape, into 4 parts. The nearer to the base, the temperature will be very close to the base temperature. This part is having the same, almost very close to the base temperature. Now when it comes to the second part, the temperature has decreased. Temperature of the fin has decreased. Again, the temperature it is decreasing, and this green color I represent for lowest temperature. So when it comes to the end, the temperature has considerably decreased. Now the heat is flowing from the base to the end. The heat transfer is taking place through the fin. Now we can see that the end, the temperature is less, and the convection from this part, since the temperature difference is small, the convection taking place is considerably less compared to this area where the temperature difference is going to be more. The temperature is high here, ambient temperature is TA, the temperature difference is going to be high. Now this part, the temperature is high and the temperature difference is more, and the convection heat transfer from this base side, it is more compared to the end or any other part. So that since the temperature is dropping, when it comes to the end, it becomes less efficient in convecting the heat. So this part is not efficient as this part in convecting the heat. So the efficiency considerably decreases to the end. And even if you remove this part, this green part, the heat transfer through the fin will not decrease much. So let us consider another case where the temperature of the fin you are able to maintain same throughout as the base temperature. Okay, the temperature is not dropping. A theoretical case where the temperature is not dropping at all from the base temperature, suppose it's 200, even the fin end is at 200. In that case, there is no temperature variation along the length. Every part of the fin is equally efficient in convecting the heat. So the convective heat transfer from the entire surface of the fin, and any portion of the fin if you take, the convection is taking place, and it is equally efficient in convecting the heat. And this is possible only if the thermal conductivity of the material is very high or it offers zero resistance to heat flow. In the heat conduction, there should not be any resistance. In that case, the temperature at the end also will be equal to the base temperature. So such case is a theoretical case. So that is what we are mentioning by this heat transfer when the entire surface of the fin is maintained at root or base temperature. The entire surface, if you can maintain at the base temperature, this fin is going to be much more efficient than this fin which is having the temperature to drop towards the end. So this is possible when you have a very high thermal conductivity. Theoretically, it is possible only when we have infinite thermal conductivity. So when you have infinite thermal conductivity, then the efficiency will be maximum. Now that is 100% you will get efficiency. Okay. So in other cases, efficiency will be less or less than 1. Usually the efficiency is less than 1. You will get only efficiency 100% or 1 when the entire surface is at same temperature. So let us find out the efficiency. So again, we are taking Fin with negligible heat transfer from the end. In that case, the equation is KACM theta 0 tan HML. Okay, that is a heat transfer with Fin divided by the heat transfer when the entire surface of the fin is maintained at room temperature. Okay, so when the entire surface of the fin is maintained at room temperature like this, the temperature is same throughout the fin. The temperature is same. Temperature everywhere is T0. So the ambient is TA. T0 minus TA is the temperature difference, and that is going to be theta 0. So not only at base, entire surface you have theta 0 as the temperature difference. And convection is area into heat transfer coefficient into the temperature difference. So H is the heat transfer coefficient. PL is area, perimeter into length. That will give the surface area, peripheral surface area, perimeter into length. So that will give the surface area multiplied by theta 0 is the temperature difference because it is at uniform temperature and it is maintained at theta 0 itself. So HPL theta 0 is an ideal case where the convection heat transfer is HPL theta 0. Other case, it will not be HPL theta 0 because here it is theta 0, here temperature differences drop, temperature differences again drop, so temperature difference is dropping, so you cannot use this equation. So in this case, this heat transfer from the fin is maximum. So actual heat transfer with fin divided by heat transfer with when the entire surface of the fin is maintained at the room temperature, you will get the efficiency. So you are comparing with the ideal case. So this transfer through this is KCM theta 0 tan HML. Heat transfer in this ideal case is HPL theta 0. So you are comparing this fin, actual fin. Actual fin will be like this. You are comparing this with the fin having ideal case. Okay. So that is efficiency. So efficiency maximum value is 1 or 100%. Not like effectiveness. Effectiveness should be always greater than 1. Okay. Now we'll reduce that KAC M tan HML by HPL or KAC I taken down. So you get M tan HML divided by when AC is taken down, you get HP by KACL. And you know HP by KAC is M square because M is root of HP by KAC. HP by KAC will be M square. So you have written this M square. So 1 M cancels, you get tan HML by ML. So efficiency of a fin is given by tan HML by ML. All the cases you can use this formula for efficiency tan HML by ML. While using this formula, we are neglecting the heat flow from the end. In any case, if you apply, we are taking some approximation. We are neglecting the heat flow from there, and we get the efficiency equation like this.